Our Element Fund project is very much thinking about a very hard problem we have, which is that our buildings use a lot of energy. Heating and cooling accounts for something like 40 or 50% of the energy used in buildings today. And the way we go about dealing with heating and cooling is we run a heater or we run an air conditioner. Our project is looking at a more subtle effect of what vertical walls and windows experience, but they also gain heat from their surroundings. We've realized that if you can actually design the optical properties of materials in the infrared part of the spectrum correctly, they can actually cool themselves relative to the materials we use every day in our buildings currently. So that's the genesis of the project, thinking about new material systems that can make this possible.
This is a really cool project because it involves technology that a lot of people don't think about every day. And so the big idea of this project is to create materials that will emit IR radiation, but not absorb heat anywhere else that is not in the atmospheric transparency window. And that turns out to be a really fun materials and chemistry problem, because you have to create materials that are selective emitters and selective absorbers. It turns out that the vacuum of space is very cold, and most people might think that that's sort of irrelevant. But if you can create materials that selectively emit heat, you can actually force materials to give their heat to the cold of space. We have made materials that are very good, strong emitters and very selective emitters in the appropriate IR wavelengths. And we're testing them right now, and they do appear to be radiative coolers. So these are optically clear systems that have the potential to be integrated into building systems.
I think that we're finding the ability to integrate these materials into structures that can then be measured in terms of their thermal properties. And it does work. That's the great thing about it. Material science is fundamentally an interdisciplinary topic. We have one foot in fundamental science and another in technology. And we toggle back and forth between the two. And UCLA makes it very easy to collaborate. There's no barriers whatsoever. And so that's really very, very nice.
And so this is just one example of what we think will be kind of hopefully a broader reimagining of how we imagine our buildings kind of interact with their environment. Hopefully an example that convinces people that there's more to do here.